Hello everyone, I am Saptarshi Mukherjee. I am a software engineer 3 at Google and I am a competitive programmer. So in this playlist we have been discussing the various problems that appeared in Leetcode contest 385 weekly contest, and in this particular video I'm going to talk about the best problem of this contest, the count prefix and suffix pairs. There are two versions of this problem in this contest. I'll go through a short visiting of the first version, and then I'll come to the second version where there are a lot of things which we can actually learn from here. Okay, so let's get started. This is the easy version. Let us understand the problem. We have to define, or we have to basically finish this function is prefix and suffix. It gives us two strings, not too many strings. It just gives us two strings. I'm sorry. So there are a number of strings given, and we need to say that whether one of them is a prefix and suffix of another of them. So over here in words, we have to tell, hey, is my a prefix and suffix of any of these strings? Then is ABA a prefix as well as suffix of any of these strings? So we will actually try to find out these pairs of ij such that I is less than j, and words I is a prefix as well as a suffix of words j. So you can look at these examples they have illustrated what exactly this means. You see pa and papa, so pa is basically a prefix of papa as well as a suffix of papa. So pa is also a suffix, it's pa over here. Similarly for ma, you can see it's ma as well as ma. So this p goes for this papa and this ma goes for this mama, and so we have two. We have two different instances of such pairs. Great. For ABAB, we don't have. Had it been AB and ABAB, then we could have had one, but the order is different. So the order matters. We only want if I will be, or the ith word will be a prefix and suffix of jth word where I is less than j. So if we have the opposite order, then we cannot conclude anything. We can't get anything. Now these are the constraints of the easier version of the problem. You have 50 words and each word is only up to 10 characters. So for easy version, I'll first think with brute force. What is my brute force over here? I'll go for every pair. I'll see for every pair, hey, is x a prefix of y and also a suffix of y. So how many pairs are there? If I calculate the number of pairs, I think I had 50 elements. So the number of pairs would be something like 50 into 50, 49 by 2, NC2. So 50 into 49 by 2 is the number of pairs. This is your number of pairs. And for each pair, we will have to find out the, we have to match the prefix as well as the suffix of the other element. So in two ways we have to match. So for prefix, we can say the length, that is 10. And for the suffix, again the length, that is 10 maximum. So it's 20, so 10 into 49 into 50, which is somewhere I think 2450 or another 0. 24500 I think. Yeah. 100, 49 into 5 is 245 if I'm not wrong. Yeah. So in these many operations it will be done. So we can definitely apply this for these constraints. 24500 steps definitely will pass. So your brute force will look exactly something like this. I've used Java functions. If you don't want to use starts with, ends with, you can just iterate. So I've gone through every pair. These two loops are for my pairs. Then you can just use this function, or you can start another loop where you will basically iterate in the forward order for both the strings, and in another case, in another loop outside that, you can basically iterate one of them in the forward order, the other of them in the backward order. That's it. Simply you can see whether it's contained till the end, and you can do this C++. C basically contains my count of number of pairs. So again, I'm holding it in int because my total count is 2500 actually quite lesser we have seen. It's 15 to 49 by 2. So that's it. Now the question is, what if your constraints are slightly bitter on you? You see quite large constraints. You have around 10 to the power 5 words, and each word can go up to 10 to the power 5 characters. And the total number of characters, however, is limited. It's 5 into 10 to the power 5. This is important as well. But the number of pairs can be huge, which means you cannot go pairwise. Maybe the sizes are small, but the number of pairs are huge. So you can't go pairwise. 10 to the power 5 and 10 to the power 5 is huge. And the length also can be used. So if you want to find um, different parts of a single word and want to store that separately, you want to store all the prefixes, all the suffixes, that can go huge. So for a single word of length 10 to the power 5, 10 to the power 5, if length of a word is 10 to the power 5, then there are 10 to the power 5 different prefixes and 10 to the power 5 different suffixes. So then storing the prefixes, suffixes is also difficult um, because each prefix again has an average size of 10 to the power 5 by 2, length by 2. This is the average size. Each suffix will have the average size of length by 2. So if I find out the total size, this will be 10 to the power 5 is the number of prefixes in 10 to the power 5 by 2. That is 5 into 10 to the power 9. So it's huge. I can't have so much of storage. I can't store all the prefixes separately. If I have to store all the prefixes separately, for every word of length 10 to the power 5, this is my total sum of lengths of prefixes. Similar goes for this one. So I cannot afford to store so much. Now what else can I do? We have seen in the second question how we can use tries for pattern matching. For this problem, I'll discuss tries in the second half of this video. In the first half, I'll discuss how we can solve this problem in an easier manner, because tries will make it slightly trickier, and we'll discuss that in the second half. First of all, we want to compare something like this, that hey, this is my string. Storing all these prefixes is difficult because this is my storage. How can I store all the prefixes and all the suffixes in lesser time? If I have something like A, B, A, C, A, D, E, B, C, D, if I want to store all the prefixes, all the suffixes, this is my cost, the sum of lengths. However, if I want to transform them into integers, if I want to say, hey, store them as integers, something like, if this is x1, x2, x3, x4, store them in this way. x1 plus x2 into some a plus x3 into a square plus x4 into a cube, and so on. Why? This is how basically we store, keeping number system in mind. This is how we convert to a certain number system. For every position, this is what it means. For example, if I say 1, 3, 1, 5, what does this mean? This means 1 into 10 to the power 3 plus 3 into 10 to the power 2 plus 1 into 10 to the power 1 plus 5 into 10 to the power 0. So we have these bases. We say this is 10 to the power 10 to the power 3, 10 to the power 2, 10 to the power 1, 10 to the power 0. Similarly, with a certain base which I'm comfortable with, it can be 29 because there are at most 26 characters, and sometimes we have that propensity for prime numbers. I can have this kind of an arrangement. I'll create these numbers. If I say, okay, by doing this operation, if finally, so I'm increasing this powers of a, finally if I get the number r, for this, let's say, for this much I have r1, for this much I have r2, for this much I have r3. For storing r1, r2, r3 will be pretty easy because they will be lesser in value. Plus, we can use a technique known as rolling hash. Rolling hash. So I'll say, okay, do all this operation, do this fx, this is my fx, do this fx. Fx is basically the summation of xi multiplied by a to the power I minus 1, you can say. Up to whatever length we are interested, we can have this kind of a computation. And then finally, we can apply a modulus, modulo b. This will help me keep the number smaller. A to the power I minus 1 can easily exceed my limits. So I can say, hey, find the modulo with respect to some prime number, with some large prime number, and let us store what modulo numbers we are having. For example, let's say b is 10 to the power 9 plus 7, a very popular prime number. That means I can store 10 to the power 9 plus 7 unique values now. This is a popular hashing technique. We call this rolling hash, and string matching using rolling hash, we have the popular Rabin-Karp algorithm. So using rolling hash, what can we say? That hey, whatever you want to store, if you want to remember all the prefixes and suffixes, do remember them. And remember not those strings, but their hashes. What is the best part of these rolling hashes? If I know, let's say R3, and if I want to find out R4, how to find out from R3 to R4? R4 means I want to find out the hash of this. So I can say, hey, R4 is equal to R3 plus X4 into A to the power 3. I just need to add one term and I will get that. However, in a hash map, if I have to store this thing, I need 4 operations to store the 4 characters. If I have to store a 10 to the power 5 length string, the time complexity will be 10 to the power 5. So this is an important catch over here. When we say map.put an str comma something, some x, let's say x is an integer, this can be an integer, then the time complexity will basically be, for this operation, the time complexity will be the length of the string, big O of the length of the string. But if we keep this instead as an integer, if we say we will add map.put the hash of the rolling hash of this string, comma some count, then basically this storing this basically will take big O one time. So for this particular thing, for this particular transformation, we use rolling hash. This is the significance of rolling hash. So this will definitely help us solve, with one caveat. Different values can give us the same value after doing modulus b. Different values can give us the same value after doing modulus b. For that, what do we do? If we know the b, if I know what b you're using, I can easily create some cases which will fail for your b. So for avoiding the solutions to get hacked, especially in Codeforces or computer programming rounds, what I've done is we use randomization. We try to use different b's. So you can see my solution here. I have randomized my b. First of all, I have this standard b, 10 to the power 9 plus 7. But then I am over here, I'm randomizing this a. I can also randomize my b. It's totally up to you. A and b you can definitely randomize. As a result of that, the person who will make the test cases won't know what you are using, what base you are using. This has a pretty low chance of collision. Collision means that two different strings will map to the same hash. That is, that has a very less chance, but that can still happen. It can still happen that two different strings, str1 and str2, which are different, will map to the same hash. In practice, it is not that likely to happen. Now the thing is, how can we reduce the chances of that happening? In order to reduce the chances, we can use different modular values, because this modulus is creating problems for me. So I can use a b1 as well as a b2. With b1, I will have some hash. So we can do something like this. For every x1, let's say I will get an h1a and h11 and h12, and for x2 I will have h21 and h22. So now we can say that x1 is equal to x2 if h11 equal to h21 and h12 is equal to h22. Then this reduces my chances of collision. This basically, it's very hard. It's very hard to find with two different modulo values that we are colliding at the same value. So practically this works. We can use two different modulo values and we can conclude. But again, what are we trying to find? That now remains. Let's say we know this rolling hash, we can store this. By storing this, what can we do? So let's say we are given a string. We are given a string over here. I can keep on forming my prefix one by one. We have already seen how from R1 I can form R2, from R2 I can form R3, from R3 R4. We can keep on forming that. Let's say this is one 4-character thing. And from the end also we'll keep on doing the same thing. This is a 4-character thing. So I'll do the similar thing for the end also using the same B1 or the same B2. And if I see that this H and this H dash, if they match, then I will say, okay, this prefix and suffix are matching. Then remember this H. I will remember, I will store this H. I will store this H somewhere. I will store this H somewhere. Later on, if a string comes and says, or if some string before this string basically asks that, hey, can I be a prefix or suffix, prefix and suffix of any of the strings in front of me? That particular string I will search over here. That is present. Is it present or not? How will I check it? I will again hash it. I will convert it to that integer using the same values. So definitely I know that if I'm hashing the same string, it will definitely take me to the same place. I will do it for the different values. We can basically do it. So for different B1, B2, we can basically store this as H1, H2. If I want to store the different B1, B2, this also will create its own HS1, HS2, and this I can compare whether it's present or not. If I want to compare just one of them, it makes it easier. I can compare both of them also. That's it. So now, so what's my final solution? Basically, take every string. Let's take from the end because we need to check from the array. We need to check in the array. This I basically ask, hey, is there some j which contains me both as prefix and suffix? So we can start storing from the right. Because the left will ask the right, hey, am I contained in you? So we will store from the right. So I'll store this, then I'll come to this and I'll ask that, hey, first check there and then store yourself. Then I'll ask this one that, hey, first check to your right and then store here. For checking, what shall we do? We'll basically check in the data structure, hey, am I present both as a suffix and a prefix? And what will we store? For every string, I will store, for every string, whatever prefix is matching with the same size suffix, I will store that prefix or suffix in this container. If I'm using multiple different bases that is for modularity, we call that as bases, percent modulo b, whatever b is we are using, we call that as bases. So if I am using different bases, then I'll store for them separately together, that okay, when I need a string, I need to match with both of them. That is how I'll be storing. And yeah. If both are matching, if h equal to h dash and for the other base also it is matching, then only I will remember that yes, for this string it is these are the two hashes h1 and h2 which stand for a certain string. This occurs both as a prefix and a suffix, right? So let us look at the code where I've taken only one hash for simplicity. So this is it. I have a hash map where the the first number, the key, is basically my hash. I could have kept it integer also, but I would have to typecast it later on. So I just kept it long, but it will actually store an integer only. And then here I'm storing the frequency, that how many such numbers are there. I believe that's what I'm storing. Yeah. Then answer plus equal to count matches. What am I doing? I'm basically saying that, hey, words I count it. So, okay, yeah, first I'm counting it. That this word is present how many times and update that in this hash map. So what am I doing? I'm basically computing the hash. This is my hash computation, simple hash computation based on some A and B that I have started. A is randomized and B I am not changing. B is a prime number. I'm computing S and then I'm returning the count for S, that how many times S is contained, or the hash of the given string is contained. Here I'm computing for the entire string. So this is the hash of that string. I'm computing the hash of the string here and storing it in S. Okay? So I'm doing this operation that every character that you get, multiply it by the next power of A. Next power of A. So first it starts with 1 and then I'm moving ahead with multiplication by A at every step. Next, I'm storing hashes for my next values. I'm iterating from the last to the first so that I can check the presence or whether it's contained in any of the words in the J which is greater than I. So the greater ones I'm storing first. So storing, how does it happen? I will calculate, I'm calculating the start and the end together. This is the first two lines. The first two lines contains the start, this next two lines contains the end. Yeah. And I'm moving my pointers, I and J. I represents the end of the first string, J represents the start of the suffix. So those two things I'm basically mapping if they give me the same value. If S not equal to, I'm not storing the actual string. That again is difficult, or it will be time consuming actually. It will cost me time complexity. So I'm just comparing S and D. I'm saying, hey, if they're not equal, then continue. If they're equal, then update this. Update this count. Update this count to 1. So this is basically the count of this prefix or this suffix. So why am I doing this? Let's say I'm searching for ABC over here. Now if ABC occurs in two different strings, in one string let's say as ABCBA and in another string as ABCB or ABCDE ABC, okay, not the previous one, BABC, yeah. So I can say ABC occurs here also as well as here also. In both of them I will store this ABC and hence I should get the count of 2. So in my count it will, the hash map will basically store that for ABC it has a count of 2. That is what I will get when I will query using this ABC. Got it? So while query, I'm querying by the exact word. I'm saying that only get the count for the word, not by its suffix or prefix. While I'm storing for every suffix and prefix. So I'm storing it, I'm updating the hash map inside the loop. And I'm querying the hash map outside the loop. That's it. So this is a good problem based on rolling hashes, a very convenient technique. Mathematically and with some risk, some probabilistic risk, you can actually practically solve many problems. This is far easier than many other pattern matching or string matching problems. Now I'll discuss in short the second approach. But before that, what is the time complexity of this code? The time complexity of this code is I'm doing it n my n times. Count matches, you can see it's just n operations. Each operation I'm just taking out a character and doing some mathematical things. That's it. And S plus, this is just arithmetic addition, not string concatenation. So this is big O n, which means, sorry, not big O n, this is the length of the string. This is the length of the string, count matches. And store hashes also goes to the length of the string. This is nothing but length of the string, which means that my total time complexity will be the time complexity will be summation of lengths of all the strings, summation of lengths of all the strings. STRI. And what is that summation? It's not 10 to the power 5 into 10 to the power 5. It is given that it does not exceed 5 into 10 to the power 5. So this itself is a hint that somewhere the sum of the lengths of the words is important to us. So this is given that this is 5 into 10 to the power 5. Awesome. What is the space complexity? The hash map has to store the hash map has got to store the prefixes and suffixes of all the words. So prefixes, number of prefixes of a word of length L will be L. So for 5 into 10 to the power 5, I can say that is a sum of lengths. So my total sum of prefixes will also be the same thing. So my space complexity will also be the same thing. Space complexity is equal to sum of number of prefixes or total number of prefixes, you can call this total number of prefixes plus total number of suffixes. So 2 into 5 into 10 to the power 5 gives us 10 to the power 6. We are storing the prefixes only if they are suffixes. So this itself is sufficient. 2 is not needed. It's 5 into 10 to the power 5. That's it. This is the time and space complexity. If I have to express in terms of this will be my expression without the values. Now the next thing is, how can we do it in a different way? So for pattern matching, the intuitive solution is basically using tries. Using tries, if I want to check that, hey, whether some stir1 is both a prefix and suffix of stir2. Str1 is both a prefix and suffix of str2. How can I check that? If I would have to check the prefix, only a prefix of str2, I could have said similar to your question number 2. If you have not checked question 2, you can check its editorial. I've discussed how we can solve it using tries. So there you will get the basic template of using tries. If it were only a prefix checking question, we could have done it. That okay, store those str2 in a try, and then check for the prefix. You could have checked the prefix from there. If I would need the suffix, what would I have done? I'd have said, okay, store this in a suffix try. In the reverse order, you can store in a try. Try in reverse order. So string str2 you can store in the reverse order. Something like if str2 is apple, then if you want to see if le is a suffix of apple, you can say store it in a reverse order. It will give something like this: elppa, p, p and a, and then you can come with le. You can say okay, go in the reverse order, e and l. So you get e, then you come down, you get l. So yes, this is a valid node, so you will return yes. So you can check the suffix over here. But the trick is, how do you check for the same string? If you store in the forward order and reverse order in two different tries, let's say you find that str1 matches, gives us a match in try 1 and gives us a match in try 2, right? So try 1 and try 2, let's say there are two tries. Try 1 stores in the forward order all the strings from the end till now, and try 2 stores in the reverse order. And this is a common wrong approach you can end up in, that okay, if I want to see whether my S is both um, a part of try 1 and try 2, it occurs both in the forward and backward manner, then you can basically say, okay, I will check in this and I'll check in this. If it is found in both, I'll consider that yes, it is there in both. This has a mistake. What is that mistake? It is present in both, but how do I know that it is present in the same string? This stores some case strings, this stores some case strings. How do I know that S is the prefix and suffix of the same string? That is not, I can't infer that from here. I can't infer that S is a part of try 1 and try 2, and also they are part of the same word. They are the prefix and suffix of the same word. So what next? This tells me I need to do something different. Using tries, you can solve it, but you have to do slightly different things. You have to look at the question in a slightly different way. Checking for prefix suffix won't be that easy. Rather, you can say that, hey, in a string, if I look at str2, if I can say that, hey, this is a prefix which is also a suffix. This is a prefix which is also a suffix. I want to check whether this is one of the strings before this or not. So let's say this is S and this is also S. Not the hash, but the strings themselves. I want to check that, hey, is this some existing string before this? Is there some str1 which is equal to S? I want to check this. So for this, I can say, hey, store these str1s into the try. So what am I saying? That okay, when I'm coming to str2, store all the previous strings in try. Store all okay, so probably I had not been sharing it for some time. I'll share it over here. I'll just briefly summarize it. Stir1 and stir2 are basically, yeah, as I mentioned, so whether they're in the same try or not, we can find out, but whether they're in the as part of the same string or not in the forward and backward order, that is challenging to find. So this part is challenging to find, whether they are part of the same string or not. And this apple example I had shown that the reverse thing we can actually find in suffix tries, but both together finding that is challenging. So now we'll look at the correct way. So let's say if we choose this particular strategy, store all the previous strings when we are at I. Store all previous strings in a try T. Now, for each prefix in str or words I, which is also a suffix of word I, which is also a suffix. This part I cannot leave on tries. This part I have to do separately. That, okay, in a word, if something is a prefix as well as a suffix, what will I do? I will say, if it is a prefix as well as a suffix, then check its count in try. Count in try. Add by that count. The answer plus, let's say this is C, so the answer plus equals to C. Now how do we find that what are those prefixes which are also suffixes? Using a concept that is used in KMP algorithm, Knuth-Morris-Spat, an algorithm of string matching, KMP, North Morris Pat algorithm of string matching. We use the LPS concept. We use an LPS array to tell us that what is the longest prefix, or what is the maximum length of prefix that is also a suffix up to every position. So if I quickly show an LPS array, so let's say we have something like this: A, B, A, B, C, A, B, A, B. Let's say something like this. It will say that, okay, up to here, what is the maximum length suffix that is also a prefix but not the entire thing. Entire thing, then definitely it is trivial. So it will say, okay, the maximum thing, not the entire thing, is this one. This is common. So these are my LPS values. If I write here the value is 4 because this 4 is matching with this 4. Over here, I will say ABA is not, okay, up to here, yes, ABA is a prefix. So this will be 3. AB is also a prefix over here. So we will say this is 2. And A is a prefix, but CA is not a prefix. BCA is not a prefix, so we will say only 1. Next, I can fill up the others as well. AB, no, there is nothing over here lesser than AB. AB itself is only the prefix and suffix that is common, nothing lesser than that. ABA, this A and this A matches, so we call it as 1. Then this B, we call this as AB and AB matching, so this is 2. And C, nothing is matching, so it is 0. Okay, this is my LPS array. Now the trick that we can use is, how can we get all those suffixes of this entire thing which is also a prefix. We don't want the longest only, we want all of them. The trick for that is quite commonly used trick. This is definitely to be taken. This one gives us the longest. Then we have to go back. According to this, we have to go back to that position. Fourth position, that is, we go back to the third index. So this is position K. We go back to position K minus 1. So we come to position 3. 0, 1, 2, 3, 4, 5, 6, 7, 8. So from 8 we move to this. This position is also important. This tells me, hey, this is another location. This string is another, or basically 2 characters up to here is another thing that is important. 2 characters up to here and 2 characters up to here. I'm just sharing in very short how you can use this algorithm, LPS array. And again, using this, you can basically say, hey, now 2 steps backward I'll go to index 2 minus 1, that is 1. So it is 0. There is nothing here. So I stay only at these two things. Then at 0, definitely I can't go anywhere else. I can't go anywhere else. So these are the 2 positions I'm interested in. One is, for this 2, I will say AB is important. And for this 4, I will say that AB is important. These are the 2 that are important to me. None of the others are important to me. How do I get it? By this traversal. We have this ABA, ABC, many things are there, but they will not come eventually if I use this particular iteration strategy. I will get 2 things that are AB, and I will get AB. Now, do I form all those strings? Do I, for each of these positions, do I form these strings again? No. I just iterate in my try. I will just start iterating from here that, hey, you are talking about this. So for iteration, I will start from the left. I will say, okay, these are my positions. This is one position. There's another position. I'll tick them. Yeah. I will just tick them. And then 2 characters basically tells me, okay, up to the second character, I will consider it. So A, B, I have considered it. In the try, I will check. Tell me, is AB there or not? It will tell me, yes, AB has occurred before. So AB is an answer. Then I will say, okay, continue. AB is already there. Inside the try, I will say, go up to index 4. Go up to index 4. So up to index 4, you have, we basically go up to index 4 minus 1, because 4 characters are common, so we count the number of characters from 0 index. So we basically say go up to AB, that is non-try. Sorry, in the try again we are basically going 2 steps more. This is also found, this is also found, or whatever is not found, that won't be found. So yeah, we can check how many times it is present or not. So try will keep on storing the easy things. They will just store the elements, and in each upcoming element we will do that complex thing of finding out the important prefixes and suffixes and check them in the try. That's it. So this particular solution is only meant for, at least in this particular discussion, it's only meant for understanding how it can be solved using this string matching algorithms and try data structure. Definitely a bit hard to implement, but you can try. You will find KMP algorithm which uses this LPS thing, and you will find uh, the basic try implementation which you can directly inherit from there. So incorporating that, you can definitely code it. But if again you ask which is the easier way, which is the more recommended way, I think this question definitely had this particular solution in mind, because the try solution definitely takes it a bit harder. This definitely is a bit easier. We can reduce the collisions much as we want, but definitely implementing this thing is definitely one step harder than what probably the problem demanded in that 1.5 hours duration, I think. So that's it. I hope you liked both the approaches. This is a good problem. Please try to solve it at least using the first approach that I shared, and also do ask if you feel there is, if you have some doubt in the second approach or even in the first approach. Share it with your friends if you find this informative. Share it with those who might find it impactful, and do like and subscribe. See you all in my next videos. Till then, take care, keep coding. See you in the upcoming contests and the following editorials. Take care.